JPEG compression works. Here's a photo. Looks fine, right? It's about 2.5 megabytes. Now watch what happens when I drag this slider. The file gets smaller, a lot smaller. 2 megabytes, 1 megabyte, half a megabyte, and the picture barely changes. 80 kilobytes. Still looks basically the same, but if I keep going, down here, around 5% quality, something weird starts happening. The picture breaks, and it doesn't break the way you'd expect. It doesn't get blurry or grainy or noisy. It breaks into these little squares, blocky patches, sometimes ringing around sharp edges like a halo. So, a couple of questions. How did the computer decide what to throw away when the image still looked fine? And when it does fail, why does it fail in squares, of all the shapes? The answer to both is the same idea, and it's a pretty one. Let's build it up. Okay, to start, we need to agree on what an image actually is. Let me zoom in, and keep zooming. Eventually you can see them. Pixels, little coloured squares, that's all a digital photo is. A grid of squares, each with a colour. I'm going to grab one small patch, 8 pixels by 8 pixels. 64 pixels total. Remember that number? 8 by 8. That's the block size JPEG uses, and we'll see why in a minute. Now, colour is a whole thing. JPEG actually splits colour into brightness and 2 colour channels, and it compresses them separately. For the rest of this video, we're going to follow just the brightness, the grayscale version. Everything we say will apply to the colour channels too, but the story is cleaner in black and white. So here's our patch, 8 by 8. Each square has a brightness value from 0, which is black, to 255, which is white. Let me write the numbers right inside the squares. There. 64 numbers. That is literally our image patch. If I gave you those numbers, you could redraw the picture exactly. Okay? Here's the key idea. The one the whole thing hinges on. We've been describing this patch as a list of brightness values, pixel by pixel. But that's not the only way to describe it. In fact, it's not even the best way. Think about music for a second. If I play a chord on a piano, I could describe that sound as the pressure on your eardrum at every instant in time. That's, technically correct. It's also a useless way to think about a chord, because a chord is 3 notes, C, E, G. That's what it is. 3 pure tones added together. The pressure over time description and the 3 notes description carry the exact same information. But one of them tells you something, the other is just a list of numbers. We're going to do the same trick on our image. Let's drop down to 1 dimension first, because 8 numbers is easier to draw than 64. I'm going to take 1 row of our patch, 8 pixels in a line. Let's plot them as bars. 8 bars, 8 heights. Claim. Any row of 8 numbers, any row can be written as a sum of 8 special patterns. And the patterns are cosine waves. Cosine waves at different frequencies. Let me show you. Here's the first pattern. It's flat, just a constant. Boring. Here's the second, half a cosine wave across the 8 pixels. The third one fits a full bump. The fourth, a bump and a half. And so on, up to the 8th. Which wiggles up and down as fast as 8 samples can wiggle. That's our alphabet. 8 cosine patterns, and we claim our original row of 8 pixels is some specific mix of those 8 patterns. Let's check. We take the first pattern, multiply it by some number, call it the weight, and add it in. Then the second pattern, times its weight, add it in. Third, fourth, all the way to 8. And there. The bars match exactly. Take a second with this. We started with 8 pixel heights, we ended with 8 cosine weights. Same amount of information. 8 numbers in, 8 numbers out. We didn't lose anything and we didn't gain anything, we just translated. From the language of pixels to the language of frequencies. That translation is called the discrete cosine transform, the DCT. That's the whole thing. It's a change of vocabulary. Now, why on earth would we do this? The bars described our image fine. What did we get? Hold that question. We'll answer it in a minute. First, let's go back to 2 dimensions. In 1D, our alphabet was 8 cosine patterns, flat, then 1 bump, 2 bumps, and so on. In 2D, we need patterns that vary both horizontally and vertically. So we take every pair of 1D patterns and multiply them together. 8 horizontal patterns times 8 vertical patterns gives us 64 2D patterns. Here they are, all 64 laid out in a grid. Top left corner, completely flat, just a uniform grey. As we move right, the pattern wiggles faster horizontally. As we move down, it wiggles faster vertically. Bottom right corner, a tight checkerboard, highest frequency in both directions. And the claim in 2D is the same as it was in 1D. Any 8x8 patch, any one, is a specific weighted sum of these 64 basis patterns. The flat one, plus a little of the 1 bump one, plus a little of the 2 bump one, and so on, with the right weight on each. Add them all up, and you get your patch back. The 64 weights, those are the DCT coefficients. And the formula for computing them looks like this. Don't memorize it, the picture is the point. 2 cosines, 1 for the row index, 1 for the column index, multiplied by the pixel value, summed over the patch. That's it. The intimidating thing is doing the bookkeeping. The idea is just how much of each pattern is in this patch. Okay? We promised an answer. Why bother translating? Here's why. Look at 3 real patches from a real photo. The first one is a piece of sky, smooth, slowly changing. The second is a patch of grass, texture all over. The third is a patch with a sharp edge running through it, like the line where a roof meets the sky. Let's compute the DCT of each. I'll show the 64 coefficients as a little 8x8 grid, where bright cells are big coefficients and dark cells are near 0. The sky patch. Look at that. The top left corner is bright. The rest is almost black. Almost all the energy is in the low frequencies, the patterns that wiggle slowly, which makes sense. The sky barely changes across the patch, so we don't need any fast wiggling patterns to describe it. The grass patch spreads its energy more. There's stuff in the middle and the corners because grass has texture at lots of scales. The edge patch is interesting. There's a streak of bright cells. The edge picks out specific frequencies. But here's the thing that matters. For natural photos, most patches look like the sky patch. Most patches are smoothish, and even the textured ones tend to have more energy in the low frequencies than the high ones. Which means, and this is the move, we could just throw away the small coefficients. Set them to 0. Keep only the big ones, and reconstruct the patch from what's left. Let me try it. Here's our sky patch with all 64 coefficients, original. Now let's keep only the 4 biggest and 0 out the other 60. Run the sum backwards, reconstruct the patch from just 4 numbers, and it looks basically identical. Of course it does. The 60 we threw away were all almost 0 anyway. For the grass patch, 4 isn't enough. We get a blurry blob. But 10 coefficients gets us pretty close. 20 is nearly indistinguishable from the original. That right there is the compression. 64 pixel values in for 4 or 10 or 20 coefficients out. We've described the same patch with way fewer numbers. The DCT didn't compress anything by itself. It just rearranged the information into a form where most of the numbers happen to be small. Then we drop the small ones. Now, JPEG doesn't actually do it by saying keep the biggest 4. It does something a little more clever, and this is the part where the actual compression happens. It's called quantization. Here's the idea. We take our 64 DCT coefficients and we divide each one by a number, a different number for each position. Then we round to the nearest integer. The numbers we divide by, they live in a table, the quantization table. Let me show you the standard one JPEG uses for brightness. It's an 8x8 grid of integers. Top left, a small number like 16. Bottom right, a big number like 99. The high frequency positions get divided by big numbers. The low frequency ones get divided by small numbers. Why is that smart? Two reasons stacked together. One, we already saw that the high frequency coefficients tend to be small to begin with. Divide a small number by a big number, round, and you almost always get 0. So this turns most of our high frequency cells into zeros, which is what we want. 2, and this is where it gets really nice, your eye is way worse at noticing high frequency detail than low frequency detail. So even if we mangle the high frequency coefficients a bit, you won't see it. The quantization table is literally tuned to throw away the stuff your visual system doesn't care about. Decades of human vision research distilled into 64 numbers. Watch what happens. DCT coefficients. Divide element-wise by the quantization table, round. Most of the high-frequency cells just collapse to 0. We went from 64 numbers, most of them non-zero, to 64 numbers, most of them 0. This is the only step in JPEG that loses information. Everything else, and we'll see the rest in a second, is perfectly reversible. The DCT itself doesn't lose anything. Quantization is where the lossy comes from. And by the way, you know that quality slider from the beginning? All it does is scale this table. Higher quality, smaller divisors, fewer zeros, bigger file. Lower quality, bigger divisors, more zeros, smaller file. That slider is just multiplying the quantization table by a number. Okay, we've got a sparse grid of mostly zeros. Now we need to pack it into bits efficiently. JPEG does 3 more things, and I'll go through them quickly because they're not really about the core idea. First, the zigzag scan. Instead of reading the grid row by row, we read it in a diagonal zigzag, top left corner, then sweep across to the right and back, picking up cells in roughly increasing frequency order. The point is, this puts all the zeros together at the end of the list. One long tail of zeros. Second, run length encoding. That long tail of zeros gets crunched. Instead of writing 00000 52 times, we just write 52 zeros, much shorter. Third, Huffman coding. Common patterns get short bit codes, rare patterns get long ones. The exact same trick Morse code uses. E is 1 dot, Q is 4 marks. Frequent things get tiny codes. That's it. And then the decoder runs everything backwards, unpacks the Huffman, undoes the run length, undoes the zigzag, multiplies by the quantization table to get the coefficients back, not exactly back, because rounding lost some, but close, and runs an inverse DCT to get pixels. So now let's go back to where we started. The broken-looking compressed photo from the beginning. The one with the blocky patches and the weird halos around the edges. Let me overlay an 8x8 grid on it. There, look at that. The blocks line up exactly with the artifacts. The seams between blocks are visible because each block was quantized independently, and at low quality, their corners no longer quite agree with their neighbours. That's the blockiness. It's literally JPEG showing you the seams of its own grid. And the halos around edges, those come from this. A sharp edge needs high frequency coefficients to represent it. Those are exactly the coefficients quantization throws away most aggressively, so when we reconstruct, we're trying to draw a sharp edge with only low frequency patterns, and low frequency cosine waves wiggle, so you get ringing. Little ghost waves running parallel to the edge. They have a name, mosquito-noise, because they look like mosquitoes hovering by the edge. But look at the smooth areas, the sky, the blank wall. No artifacts. Why? Because the high frequencies were already near 0 there. Throwing them away cost nothing, so everything we see in a broken JPEG, the squares, the rings, the way smooth regions survive and detailed ones suffer, all of it follows directly from the recipe. Cut the image into 8x8 blocks. Describe each block as a sum of cosine patterns. Throw away the patterns your eye doesn't notice. Pack the rest tightly. That's the whole algorithm. From the late 1980s, still running billions of times a day every time you load a web page. It's kind of amazing how much of it comes down to one idea, that the language you describe something in matters. Pixels were a fine language for storing an image, but cosines were a better language for compressing one. Same information, different vocabulary, and suddenly most of the numbers are small enough to throw away. Modern formats, WebP, AVIF, JPEG, XL, they replace the cosines with smarter patterns and they predict blocks from their neighbours before transforming, and they're better in lots of small ways. But the core move is the same one we just walked through. Transform into a space where unimportant detail is easy to discard, then discard it. One last thing to sit with. The next time you see a pixelated JPEG, look at the edges. Find a sharp boundary somewhere in the image and look right next to it. You'll see them now. The little parallel ghosts, the mosquitoes. You're seeing the cosines that almost got thrown away, doing their best to hold the edge together. What other patterns can you find hiding in there?